This shows two things. One is the idea of superposition, that a cat, following the basic prescription of quantum mechanics, at least in principle, a cat, you could realize a situation where a cat was both dead and alive at the same time. This also shows the property of entanglement, which I'll come back to in a second. I think the main thing to say is that, and probably repeat what Serge said, is that the thing that, even though Schrödinger being one of the inventors of quantum mechanics, he was bothered by the kind of the logical conclusion, that is that the founding fathers, including Schrödinger, thought about in terms of simple, small quantum systems, but quantum mechanics by itself you should be able to extrapolate it up to large systems like a cat, and that bothered him because we obviously don't experience situations like this. For the non-specialists out there, one sort of analogy I like to superposition is given in this example here. So if you look at this picture here, you can, at some instance of time, you might be able to see, for example, this surface here in the foreground, or this surface here in the foreground. That is something like that. And so this is kind of a nice illustration, I think, of superposition, in the sense that this image up here has both properties at the same time, therefore giving this idea of superposition. And another thing this example illustrates is when we talk about quantum mechanics and when we do a measurement on some quantum system, then we project or collapse the system into one of its two possible states. So that when you look at this figure, if you see one or the other faces of the cube being in the foreground, then that's like a quantum measurement, in the sense that before that has both properties, and then you seem to collapse onto one view or the other. So this, I think it's a nice illustration of this idea of measurement in quantum mechanics. So just if you'll play along with this example, an analog to quantum entanglement is where you might have two systems, in this case the two boxes, and at least for myself, even though they represent each box represents the two situations like I mentioned on the last slide, at least for myself, when I see one of the surfaces go into the foreground, I tend to see the same surface on the other cube going into the foreground as well. And this, at least in part, represents this idea of entanglement, where these two boxes are entanglement in such a way that when we measure, that is, if we see one of the surfaces being in the foreground, then the other one is also correlated with what we see on the first box. And in fact, coming back to Schrödinger's cat example, then this is also an entangled superposition, in the sense of because when the particle is undecayed, that's correlated with the cat being alive. Similarly, when the particle decays, that's correlated with the cat being dead. Okay, so as I say, this idea of extrapolating quantum mechanics into the classical regime certainly bothered Schrödinger, and one way out of this dilemma for him, he said, well, look at, in some sense we cooked up these thought experiments thinking about small quantum systems, and at least this bizarre situation of the cat being dead and alive. Well, maybe we're misleading ourselves, and so he said, well, maybe the problem is we really can't experiment with single atoms or molecules, so we're leading ourselves astray by thinking of those situations. Well, in fact, we can now, and the techniques that Serge's lab and our lab and many other labs have been developing over the last decades are now allow us to play these games, at least where on a small scale we can make these weird situations that are analogous to Schrödinger's cat. But to do that, what we and many other people have had to do is to just get better control over the systems we play with. So we need precise control over these atomic, or in Serge's case, electromagnetic systems. To do that, we need good isolation from the environment, and they become more manifest, at least at the current time, with small systems. And so, to get to these situations we're playing with now, we really had to kind of tackle all these things at the same time. So I'm gonna give a little bit of a personal history. Actually, one nice thing for me, the way the citation of the word read was, it really describes my whole career in some sense. So I'll give you some examples from my viewpoint. But again, I stress that this business is the contributions of many people over the last few decades. So anyway, I was a graduate student in Norman Ramsey's lab in the late 60s. And this is Norman here. This is me trying to get close to the boss. But anyway, this was at a time shortly after the time that Norman and his colleague Dan Kleppner had invented and demonstrated the hydrogen maser. So at the time I was there, Norman wanted to have accurate measurements of the hyperfine frequency that the maser is based on for all the isotopes of hydrogen. And so my project was to set up a maser and measure the deuterium hyperfine frequency. And I always like to muse about that. I'm probably the only one in the universe that has that number memorized, because it was the main result of my thesis. Nevertheless, in terms of the context of the subject here, what it taught me was, first of all, we have to be, when we measure these frequencies with high precision, we have to be very in control of the environmental effects, either to be able to control them or at least measure the effects very well. The other thing is that kind of naturally in these maser systems, at least in the microwave low frequency region, we're making superpositions. When the atoms are inside the maser cavity, these atomic superpositions, they're slowly changing in time, but nevertheless they're coherent superposition. And in that case, they're actually living a fairly long time, on the order of a second during their time inside this maser cavity. The only difference is that this is on very large numbers, so one thing is to try to get down to much smaller numbers of particles that show these superpositions. So when after getting my degree with Norman Ramsey, then I went to Hans Stammel's lab at the University of Washington, and Hans actually was thinking about a couple things. One is he had done some high resolution spectroscopy on atomic ions versus neutral atoms, but his main focus when I was there in the early 70s was that he was after measuring the magnetic moment of the electron to high precision. And so one way to get at that was to be able to hold electrons in one place and examine them. And so schematically, the way to think about it is we have some electrode structure. With the electrons, we use both electric and magnetic fields to hold the electrons. But what you can think about is on a pretty close analogy, it's these electrons in the trap, we call it, are very much like a marble in a bowl. And the same situation will be true for the ions. One nice thing about this system is we can think about the electron in this trap as being like it forms an equivalent circuit, which is like a tuned circuit. And for those that aren't familiar with the tuned circuit analogy, you can still think about the marble in the bowl. And what we do to detect the presence of electrons in this trap is that we simply apply a potential to one of these electrodes, and that excites the harmonic motion of the electron, and we can sense the current induced in the electrodes by the electron's motion by just dropping the current over a resistor and amplifying the signal and reading it out. And the reason this was interesting is that during the time I was there, we realized that at least for a high accuracy measurement of the electron's magnetic moment, it would really be desirable to go down, rather than an ensemble of electrons, use one electron to get rid of the mutual perturbing effects of many electrons on the trap. So in these early experiments, the way we could get down to one electron is that we would adjust this potential on the electrodes to be such that the electrons were excited to a high amplitude, and occasionally one electron would gain enough energy to hit the electrode and be lost. The analogy with a marble in a bowl, you can think about that we were exciting the motion of the marbles just to the point where occasionally one would pop over the edge of the bowl and be lost. And so we could get a signal like this. This was a case where we started out with 7 electrons, and when we adjusted to this critical excitation potential, we would see the electrons occasionally move out